Thank you very much. Thanks, Roland. Thanks, everyone. I'm very honored to be here, even if it's 2 years later, as you can see. I'm very happy. I haven't been traveling for a while, so I think it's good to use this occasion to come back. Let me just thank my group before I start. You will see them again. You will see the individual that are responsible for the project that I will discuss, but everything I will present is, of course, thanks to them. And let me tell you a little bit about what I'm going to talk about today. There's something you don't know, because it's probably not very important, but when I built my laboratory in 2008, I was asked to give a name for the lab and an acronym for the lab. And I was a little bit rushed. I knew I wanted computational. I knew I wanted molecular, because I'm very molecular-centric. And I added the D, so you see up this LCMD acronym that stands for Laboratory for Computational Molecular Design. And I realized after a few years that we were not designing anything. So I decided to, either I needed to change the name of my lab or I needed to start designing something. So that's why you have here this workflow. It's an inverse design workflow. And what I will discuss is a little bit the effort that we place on some of the components that are necessary to have this kind of workflow running. All the application and also the technical development that you will see are centered today on catalysis. And the reason for that is that you might not know, you know perhaps that in Switzerland we sell a lot of chocolate and cheese. But what you maybe don't know is that we sell much more coffee than chocolate and cheese. Those figures are a little bit old, but they are still true. So much more coffee than chocolate and cheese. And you might also know the country or not for the luxurious watches, but we actually have a much larger share of exported chemicals than luxurious watches. And since chemicals, 90% of the chemical needs a catalyst to be synthesized, the country is very big on catalysis. This is true worldwide, but perhaps even more in a country as small as Switzerland. So catalysis is a big thing, and that's why the example that I will show you today are related to catalysis, also because it's an important topic, of course. So let's go back to my little workflow here. I will start discussing what you have on the top. Okay, you want to find a catalyst, which one is best? So there are two questions that you will ask yourself, is how to formulate the property that is necessary to predict, to identify if the catalyst is better or not. And that will come a little bit later. And once you can formulate that, you will have a property usually based on some kind of reaction energy that you need to predict. And if you want to repeat the cycle many, many times because you are in a design type of workflow, you need to do that rather fast without losing the accuracy. And this made me think about Löwdin, of course, because that's some of the paper that he wrote that I like the most on correlation energy. And I realized that I sometimes think I'm still young, but I'm not that young anymore. And I already went to true revolution in the field of electronic structure. The first one, I started my undergrad in '98, and some of you, at least the oldest of you, remember what happened in '98. It was the Nobel Prize for density functional theory to Walter Kohn and John Pople. And I was a fresh undergraduate student, and I was hesitating at the time between chemistry and physics, so I was really fascinated by this Nobel Prize given to DFT. And I never had the chance to meet Löwdin because he passed away in 2000, and I went to my first conference, a memorable DFT conference in 2001 in Madrid during 9/11. That was a memorable one. And after this DFT conference, I went to a little bit broader conference in the field of electronic structure, and I realized the tension that existed between the people going for DFT and the people going for wave function-based method. This tension was actually never stimulated by child from the Löwdin school, I will say. It came a little bit from people a little bit more from the south than here, without mentioning necessarily which country. But anyway, a lot of tension, which was surprising to see. And then second revolution, I put 2013 QML for physics-based machine learning, or machine learning in general, but it became very popular also in the field of electronic structure. And as you can see, I started with TFT and I go less and less accurate, you might think, and it doesn't matter. I think the mindset that we are still, and the type of intellectual reasoning that we are still having remain the same. This is my impression. And I think we still try to keep that rigorous as possible. And I give this example of Anatol here because I was supposed to give this lecture 2 years ago, also together with Anatol von Lilienfeld. So I want to pay tribute to him also in a few slides that you will see. So we go less and less accurate because sometimes if you need to repeat an operation and have access to a molecular property many, many times, it might become advantageous to bypass the resolution of the Schrödinger equation, of the Kohn-Sham equation, and to use a statistical model that can provide you the same information at a lower cost. So that's why where I am going to take you. And one final slide from the beginning of my career. When I started, I was working a lot on trying to insist that London dispersion are relevant not only between molecules in van der Waals complexes, but also within molecule. And at that time, we were showing a lot of these bar plots that were very popular, and that was the figure of merit. Today, the figure of merit are more this learning curve, and going back again to Anatol, that are very relevant in the field of kernel-based machine learning model, where you see that the model, or the so-called representation, so the representation is the vector that encodes the molecular structure, if you want. The one that is the most accurate is the one that leads the steepest slope, because you will need less molecule for the training to reach the same accuracy. And all these acronyms that you see here are those kind of representation. They are often, but not always, nonlinear function of nuclear charges and coordinates. One that I like a lot, and that I will discuss a little bit in the rest of the talk, is Slatom, that use one body, two body, and three body potential. And I like it first because it's actually very hard to beat for many type of molecular property. And the bonding term here, the two-body term that is here to mimic the chemical bond, is represented by a 1/R6 potential, which is the London type potential, which is a bit controversial in itself, but that connect well with the work I did also on London dispersion. So here is an example of some of this representation that you see. They are physics-based because they are based on nuclear charges and coordinate, the same information as you will have in the Hamiltonian, and also because they contain some kind of a constraint, symmetry constraint, injectivity, they obey injectivity, equivariance, and criteria like that. Very quickly, so this vector will then be injected into a similarity kernel that can be a Laplacian or a Gaussian, and that will be used to measure the similarity of the vector associated with a new molecule to the one in the training set. So this is a very popular plot now, and within the field of molecular property prediction, there has been a lot of work that has been done and a lot of progress to achieve representation that can reproduce or predict molecular property, like here the typical example of quantum chemist atomization energy very well. But where the field hasn't advanced so much was to reproduce property that are relevant to chemical reaction, so that involve not only one molecule, but several molecules. And for me, I remind you that I will take you to some example within the field of catalysis, and we're interested in reaction-based property more than molecular physics-based property. So here there is much less example within the physics-based machine learning field, and there's some challenges because there are more moving pieces. Of course, you don't want to inject the structure of a transition state to reproduce, to map with activation barriers, because locating transition state is an experience in itself, and if you have it, you probably don't need statistical model. So we have to find a way to manipulate this kind of, let's say, product and reactant into a physics-based model that resemble those that are used for molecule, but that, in a sense, more suited and more dedicated for this purpose. So that was our objective. And there was very few precedents, including one from our own group, where we realized that in 21, that if we take slatum and if we take the difference of the slatum representation of the product and the reactant, the accuracy is way better to reproduce activation barrier than if we take the slatum of only the reactant or only the product. The problem is that the slatum representation scale has n cube, and if you take a difference, it's a little bit frustrating to have two things that have a lot of features that you then subtract to one another. It looks a little bit like an overkill. So we wanted to see if we can have something more compact. Here is the dream team that worked on this project on designing physics-inspired reaction representation. I will show you two flavors, one where we really design it and one when we let the model finding which type of representation is adequate. This is not an exciting slide, but it's a very important one. It's showing you all the data sets that were used to validate and to verify the accuracy of the representation that I will present. They are very diverse. There is the GDB set that contain really a lot of diverse transformation with super large range of activation barrier. There is a much smaller set, propagule, that is very sensitive to get right because it is about stereoselectivity and enantioselectivity, but the chemistry is very stable. Another one that is challenging the hydroform because it's multimodal due to the fact that we have various transition metal involved, and a much simpler one, but that is kind of useful for a proof of principle, which is the SN2 set that is the only one for which we predict thermodynamic rather than kinetic property. So I remind you what we want is a model that can reproduce this well, and we evaluated what are the design principles that we need to incorporate in this new dedicated reaction representation. And the first thing we realize is something I told you better early, is that if we have a representation that is additive, it's very important because taking the difference between reactant and product makes real sense. So here, slatum is additive. Soap, another variant that is based on density, is additive. BOP, bag of bond, is not additive because it uses internal coordinate. So having additivity really helps because you see here, that's in orange, it's the difference. In blue, reactant. In purple, the product. And you see that systematically taking the difference really helps. So we need first design principle, additivity. Second design principle is that since it's a reaction that you're trying to map or to capture, the most important thing is really forming and breaking bonds. So you can focus on the two-body terms, which are here to represent that. The one body will kind of cancel. It's which atom type is present. And the three-body is less important for capturing bond breaking and bond forming. Here you see it. You have in blue the slatum of just the reactant, really not good. You have the slatum diff in orange. But if you take just the two-body term, you already reduce the number of features and you're still relatively accurate. So that's the second design principle that we identify. The third one In Slatom, the pairwise feature are regrouped into bags. And this is very convenient because if you do a diff, you will have a feature, for instance, in this SN2 reaction example. If you break the CF bond and if it disappears, the feature in the reactant and in the product will align, and the signal will be very strong if one bond is broken or formed. So two features should be separated with bags. This is something that we wanted to keep. So I won't go too much into detail of the variant, but what we came up with is this B square R square variant of bond-based reaction representation that actually use all the three design principles that I showed you before. And what it does is that it, in a sense, simplify a lot the Slatom diff two-body version so that we can have variants that are dedicated for reaction, for mimicking reaction property, and that also contain much less feature. We have three variants of that. One that use pairwise bag that scale as n square. We try also a version that use bags based on element to reduce the number of feature, and we also try to drop this bag approach to even have less feature. And here you see the result. So for the propagil set, the one that is very difficult to get because of enantioselectivity, we have 7 elements, which means that the number of feature with Slatom will scale as n over, cubic, and you see that you have 28,000 feature here. So what B square R square does is that it really limits the number of features, trying to keep the accuracy as close as possible from this Slatom variant. Now this works relatively well for some of the challenging set, like the propagil, but looking closer at the GDB, that's this data set that contains a broad set of reactions. There was a precedent that were considerably better than us, and this precedent was using ChemProp from the group of Bill Green and others. This is a 2D graph neural network that contains atom mapping. So atom mapping means that it can follow actually which the atom that are in the reactant in the product, in what are they transformed. And if you look at for the GDB set here, even a 2D based neural network, graph neural network, does a way better job than what you have here in green, which are the physics-based representation, or in red, which are the Morgan type fingerprint. That's not necessarily true for this challenging propagil set or this other example that is a cycloaddition type of set, but really for the GDB, there is still progress to make. And the take-home message, if you look at these 3 different sets, is that 3D geometry, that's something we want to keep, because for enantioselectivity we won't be able to do without. But including atom mapping can be something that helps, and that's what we think we see here. So we decided, and here you see the real importance of atom mapping in ChemProp. If you remove it, you reach an accuracy that is similar to the physics-based model. So what we try to do then is to combine these two worlds and to have, in a sense, both something that is physics-based, based on 3D geometry, and that's this equivariant neural network that Puk and Xenia design, where the representation, if you want, is also learned. It's symmetry adapted, so we have all the equivariance component. Then we can assemble, that's just schematic, but we assemble the representation of the reactant and product into a reaction-based representation also, and we can predict the property. We have an invariant that's called inReact and an equivariant that's called equireact, depending on how far the spherical harmonic are included, that we have these 2 options are viable. And we have also an option that's very schematic, but with no atom map to verify the relevance of atom mapping, a vector mode that corresponds more to a global representation, and an energy mode that corresponds more to a local, so atom center representation, where all the atom contributions are summed up at the end. That's why these two different modes represent, and that's what the no mapping or mapping, explicit mapping or mapping that is learned represent here, to go very quickly. So what you see here is that, again, this GDB challenging. Chemically, it's not very challenging, but to learn well with physics-based ML model it was, you see that with the atom mapping, 3D React, which is our neural network, here it's the invariant model, by the way, can finally match something like ChemProp without losing the accuracy in the propagule test set that really require this stereochemistry. So geometry and atom mapping are indeed very important. And for 3D React, it remained very difficult to achieve, for instance, let's say real live test set that are interesting to the chemists around us. One final word, because I think it's technically important, when we compare, so 3D React, I told you it has an equivariant version and an invariant version. Equivariance is known to be quite useful sometimes for molecular property to improve the accuracy, even if the properties that are learned are not necessarily equivariant with respect to rotation or translation. But here in reaction, we saw no difference. We're still trying to find example involving chirality where equivariance might help, but for this case, it didn't help. So I basically show you the first part, which was how to evaluate accurately and relatively rapidly. I didn't give you time. Once the model are trained, it takes less than a second to actually predict the property. But the question is now which property I want to predict so that I can tell you which catalyst is best. And I need to go to this step quickly before going to the real application example. And that's the theme for this second part. And NaviCat is actually a platform that we have developed to navigate catalyst landscape. It includes many different tools, going from a volcanic that can construct volcano plot that I will use a little bit automatically. We have a macrokinetic variant of those volcanoes. We have Mark, which can post-process all the conformer and use only the relevant one if you do a conformational analysis. And we have NaviCat GA, which is the genetic algorithm that we are using. And to determine which catalyst is best, I think you have been, for those who have been following our work over the last few years, you know that we use a lot this volcano plot. We rely on compromise. Everything in life involves compromising. You have example here for the US media, where you have CNN on the left, Fox News on the right, and you see that the media that is the most reliable here is the one that has this less amount of bias, right or left. Here you also have the brain of a mathematician. Mathematician, you know that they are at their best when they are very young, younger than 30 years old. And that's because later, at the later stage of their life, their brain become biased and they cannot have any breakthrough anymore. So that's also a kind of compromise. And we use the same idea for catalysis. I mean, we're not the first one. That's one of the first volcano plot by Trasati in 72. And it's really Jan Noskov in Denmark who popularized this idea in the field of electrocatalysis, where it's casting the Sabatier principle, right? You cannot have something that binds an intermediate too much because it will not be able to release it. And you cannot have something that releases too easily because then it won't bind. So ideally, you want each step to be balanced and equivalent. And what we have been doing over the last year is to demonstrate that this concept works also for various examples of catalytic cycle in the field of homogeneous catalysis. So we will use these tools, and now we don't build anymore the volcano plot ourselves. We release these volcanic tools that can very easily skip all the painful step and give you the volcano based on a rather easy input. And we have either those volcano plot or the two-dimensional example having two descriptors that we call activity map. And that's what I'm going to use now. So it's quite convenient, because if you identify a descriptor that can basically connect to the catalytic cycle that you are interested in looking, you can then use a ML model to predict this descriptor very quickly. You can, with this map, it's like a geography map, when you want to know where is the highest mountain, so you know exactly where is the region of highest catalytic activity, so it's very convenient. And you can also use that as a fitness function in a optimization, in a closed loop optimization, so that you can drive the optimization directly to the region that you are interested in. So that's what we are going to use. And for what which example I picked this example that was basically drive forward by Shubhajit Das, a former postdoc in my lab, on frustrated Lewis pair. There will be some reality check and some design. Finally, we design. And the big fish in the field of frustrated Lewis pair is Douglas Stephan in the University of Toronto. And the nice thing about this frustrated Lewis pair is that it basically mimics the chemistry of transition metal, and it has been very successful for various substrate scope. But for CO2 as a substrate, for the hydrogenation and CO2 into formate, there was no example of catalytic turnover, only stoichiometric. So that's why we decided to tackle this task. And the two questions I will try to answer is that how to find the suited combination of Lewis acid and Lewis pair. And since we don't want to have them floating around, how can we find a way to anchor them into MUF to have a more solid type catalyst that is more resistant throughout the cycle? So the two questions I'm going to ask, the first is the chemical one, which in terms of chemistry combination of Lewis acid and Lewis base do I want? You have here a catalytic cycle. The two key steps are the H2 attachment and cleavage. It has to be able to attach. And also the release of the formate. It has to be able to be released. So here's the catalyst pool that we use to build this map, this activity map that I mentioned before. Quite a lot of Lewis acid with those boron and the substituent, and Lewis base made of nitrogen or phosphine. And the descriptor that we identify as being good to build the activity map, and that can be the base for the machine learning model, for instance, or computed if you can afford the computation, are the free energy of proton attachment, FEPA, for the base, and the free energy of hydride attachment, FEHA, for measuring the acidity. And based on these two descriptors, we got this map here. So more negative, more acid or more basic are the two species. You see that if you're in this region, you have problem to release formate. If you're in this region, you have a problem to activate hydrogen. And that's the region where you want to be. And what we realize by building this map is that experimentally, that's where experiments were going. And you really need a cumulative acid-base strength. So if you use a strong acid, you need a weak base. If you use a weak acid, you need a strong base. And the tendency was actually to use strong acid and strong base. So experimentally, they were consistently in this region. So we identified this one in the inverse type of Lewis acid and Lewis pair, which correspond to that. And we ask our experimental colleague, we don't succeed very often, but this time we succeed. We ask them to try to actually do that. And that's one of the first time where they did it without complaint.
here is the example of their actual experiment. And it did work. That was the first report of catalytic turnover by using the combination of this relatively weak acid and strong base, which was kind of an achievement for us too, to have our experimental colleague able to synthesize and kind of design. Second question, before I go to the whole workflow, it's the geometrical constraint. So now we know which chemistry is suited, but within a MOF or within a porous material, the orientation, both distance and angle, can influence the activity a lot. So here we build another map. You see which distance is ideal and which angle is ideal between these two Lewis acid and Lewis pair. And that's a delta TOF, so it's a delta of turnover frequency compared to having you acid and pair completely free, right? So without constraint. And you see that you can really increase the activity by imposing the proper constraint. That's why it gets red. And with this map, we were able to identify how to adjust the two components in this multi-component catalyst variant, and how to best adjust them using this map. So now that we have descriptor for the chemistry and descriptor for the geometry, the distance and the angle, we need to put that into a MOF. That's the final work that we needed to do. And what we did for that is that we actually screened for some organic linker that contain a benzene and a sp2 hydrogen that can be functionalized potentially through coupling experimentally, right? In the computer we did easily with the acid. So all the linker that we selected contain a base already and a position for functionalization to incorporate the acid. So here is the workflow, how it went. We curated the Corminboeuf database from 2019 that contained about 14,000 MOF. We identify the linker, as I told you, that contain a base and a benzene group. We identify the coupling site. We then functionalize with 3 types of acid. We then identify which one are actually relevant, like in a sense there was no big indifference or superimposition of atom. And this led us to quite a broad diversity in terms of chemistry and geometrical environment. And once we had these 17 or 18 catalysts, we actually screen using the geometrical criteria that I showed you before that reduce considerably the number of catalysts, because you see that we need to go to have an angle that is larger than 70 degrees. So we didn't have much left at this stage, only 400. Then we use the map for the chemistry that I showed you before, because we know that we need this cumulative strength of the acid and the base. That led us to only 80. Then we had to make sure that the space that's measured through the pore limiting diameter, once we insert the acid, the diameter of the pore can still let a CO2 entered in the MOF. And that was this, here we train a ML model using the one from Serensky, a similar model that we train, and tried to combine 81 linker that we designed with about 53 metal. And that led us to actually 47 candidates. But I think what is more important than this number is the design rule that we came up with, because they were all designed in the computer. Even if we build a MOF afterward, we identify the type of position that the two species needs to have in the linker, and we identify also the type of chemistry that needs to be assembled to follow the inverse type of frustrated Lewis pair or the normal one. So all these possibility that would actually work. For one of them, we built the MOF and show that it actually seems reasonable. No one has yet synthesized it, but I think the guidelines are now there. And with this, I think I should be closer to my time. I want to just come back to what I've been telling you. Well, I started by showing you some reaction-based, physics-based reaction representation that mimic a little bit all the work that has been done for molecular property. We are still fan of volcano because we don't know how else to do to tell which catalyst is best. So for us, it's remained very useful as a tools. We placed effort on design. So we have been designing quite a lot of things over the last 6 years, I will say, and I think we will continue. Something I haven't discussed today, it's the vice versa. There's a bunch of things we are doing in the lab where we actually use quantum chemistry to get inspired with our ML model, and I haven't discussed that too much. I also haven't discussed the building, the strategy to build database. That's something that was in the short talk for students, but it's super important, and other speakers of today are also placing effort into that direction. And all these things are in, all this effort here are in another package that we are developing that is called QStack. And with that, I want to thank all of you for the honor and for having selected me to deliver this lecture. And of course, thank you to all the group members who did the work that I have been presenting today.
Better? Yes. Okay. Well, thank you very much for this wonderful lecture, and we have some time for questions. Philip? Or, yeah?
Yeah. I have a question about the descriptors when you calculate volcano plots, and I'm curious to hear about what they are. So I do not want to think that the way how you plot the volcano plot has to mean that there must be 2 descriptors and not 4 or 1. So what I'm wondering about is what if there are none, or what if there are more than 2? Or in other words, how do you find these descriptors before you actually do that analysis?
Yeah, so most of the time we used to build volcano with 1 descriptor that was one of the reaction energy of the catalytic cycle. Mm-hmm. And what volcanic does is that it takes all the energy of each reaction step and check which one, not each reaction step, but with respect to resting state, if you want, mm-hmm. and check which one correlate the best with all the other. And that's what we used to take as a descriptor because, for instance, for Suzuki cross-coupling, we like to take the oxidative addition because in our understanding it represents how strong the catalyst will bind the substrate, so it's very intuitive. So oxidative addition is one example, and it's a step that correlates linearly relatively well with the other. I went quite fast, but in the example I gave you, the geometrical activity map, that's the first volcano that we built that doesn't contain, that is not built based on linear scaling relationship, but on non-linear one, namely Morse potential, because if you go away from energy and use geometry, you might have dependency that are then not linear. But I would say that so far the way we identified the descriptor were based a lot on intuition and understanding. We haven't yet done that using artificial intelligence. Right. It's all based on human intelligence so far.
Cool. More questions?
Yeah, I have one.
Yeah.
Of course. So this is very, very interesting, and you're starting to see theoretical chemistry actually address relevant industrial problems or logistic problems that society sort of are experiencing. I, on the other hand, I like to twiddle with my quantum chemistry as much as possible. I do some machine learning, but I might become irrelevant. So my question to you is, what would you like theoretical chemists that do hardcore theory, in what way should they do development that assists you in your endeavor trying to do real chemistry? Where can we contribute and be meaningful?
Yeah, I think it's a bit, the answer to this question is a bit there. Things I haven't presented today, where we try to think about everything we learn from quantum chemistry, metrics, physical constraint, guess Hamiltonian, and how we could actually use that, embed that into some kind of still physics-based machine learning model. And this is something that I think the exercise for you will be the same intellectually, because I know what you will like to think about. But there are many things that we have been learning in DFT or in wave function-based method that are actually applicable to the design of ML models that are purely based on physics. And I think this is something cool, because if you incorporate physics in a better way, you can use less data, you can actually have models that might be more accurate, because molecules, they are not like a random object, that they contain symmetry, they contain some physics. It's not like an image of something that is random. So I think that's where we are trying to do this effort in QStack, but I think that's one of the aspects where quantum chemists are essential.
Thank you. I'll toss it to you, and then you toss it over here.
Thank you very much for the nice talk. So I have a question on, in the latter part of your talk, the data sets that you stated there, were they calculated by your group, or are they public data sets? And a related question, so when it comes to the computational effort, so what is dominating? Is it ab initio with DFT calculations, or is it the training of the models?
So for the data set, I had the references, but it's true that I haven't mentioned it. Two are from our group, the very specific chemistry, like propagil or hydroformylation, those comes from our group, and the more general one, the GDB comes from, the GDBTS comes from the GDB database, and the SN2 was from Anatol Finn-Lellenfield. So we have a combination of origin of data set, but it's true that for reaction property, there were not that many available. Now there are more and more, but compared to molecular properties, so quite a few comes from our group. Now to answer your question, is it the quantum computation to get the reference data that costs more, or the training? It's the electronic structured data that we need as reference data that still costs the most.
Okay, thank you. Thank you.
Clemence, thank you for a very nice talk. You showed these results for these reaction processes where you used Slatum, and then you made approximations to that. So you made like a tailored representation where you only retained the two-body term. And you said that the three-body term, or the terms...
Help a little bit, but not...
They mattered some. So I'm just thinking, like, once you have a reaction or a molecule undergoes some kind of transformation, you have some relaxation effects. So I find it curious that you only need to account for the bond breaking, but not these other structural changes that go on? Because I would think that that's where the free body terms would really matter.
They matter a little bit. I mean, as I show, the result with the three body was still a little bit better than the two body.
Yeah.
But I think the problem we had is that we had this Latham vector, which is super huge, large number of feature, and you do a subtraction of two large things that remain large because it's regrouped into bags, so no way you can reduce the number of feature with a subtraction. But then as a compromise, because we like to compromise, the two-body variant was for reaction, the thing that was very reasonable. But I think for molecule also, the three-body terms helps, but the majority doesn't come from the three-body.
So if you have large relaxation effects, and these are not captured really in the current Latham representation, when you do the diff of that, could it be that what you really want are like more sophisticated free body terms or representations of these changes?
That could be. The thing is that, the number of data sets are viable to validate if it is right wasn't there. But if there were many different type of data set that can actually verify if this is true, that will be a verification to be done.